There are at least 3 operating performance goals in surface water treatment. They include filterability, dissolved organic carbon reduction, and settleability. Jar testing can be used to determine the best coagulant and dose for meeting all 3 treatment performance goals. However, most operators and engineers were taught only to evaluate floc settleability and not consider the strength of the floc for filterability and dissolved organic carbon reduction. Jar testing procedure and analysis presented in this video addresses all 3 performance goals that provides the supporting data needed for operators and engineers in selecting the best coagulant and dose for overall full-scale plant optimization. All right, earlier we discussed how to calculate the stock solution, how much chemical we're going to add for making, say, a 200 ml stock solution. So we have our pipettes. I have different pipettes. This one ranges from 0.1 to 1 milliliters, and the other one ranges from 0.5 to 5 milliliters. So on this one, for this jar testing example, we're going to use acid alum, and I'm going to make a 2% solution based on my dose range. I'm going to be dosing today, it's above 50, so I don't want to have to pipette twice per jar, so I'm going to make a 2% solution. That's going to be, that 2% end up being about 8.44 mils that I need to pipette out. So I'm using 200 mil. I'm going to first thing add some distill water. You can use distill or DI water. And I'm over a sink, and I'm just going to fill it up about halfway, a third. And then I'm going to take my coagulant, and this is acid alum, 7%, sulfuric acid, 36.48 alum. I have my pipette. You have your tip, or pipette tip, and then I'm going to set it to, I'm going to do, so if 1% is 4.22, so I'm going to pipette twice. I'm going to pipette 4.22 twice in here to make 8.44 to give me a 2% stock solution. So be sure you know how to use your pipette. There's 2 stops here. First stop is you go down and you slowly bring it up, and then when you pipette, you go all the way down, then you dispense to the second stop to ensure that you dispense everything. The first thing when you have a new pipette is that you want to be sure it's wet at first, so you pipette the first time and then just dispense it out back into the coagulant, your product, and then now go ahead and pipette back in here, and then I'm going to dispense, do it one more time for 2%. And then we're done, and then release your tip. Then I like to kind of mix it up a little bit before I finish adding my distilled water. Oh, I won't add it all the way to the line. We're going to go up to this line here that makes it 200 mils. And then I'm going to use my squirt bottle that has also DI water to finish adding it to the line, which makes it much easier to do. And then we are. And then I'll mix it up again. And then I'll mark this flask with what's in here. I'll put down 2% acid alum. Acid to lower the pH. And the reason they do that because the alum works better. It performs better at a lower pH. So that means you have separate feed system. You have a feed system just for the alum and a feed system for the acid. But some plants, they don't want to have two separate feed systems. They could buy the coagulant that has already the acid already in it, and so they're adding it as one product. So they have alum plus sulfuric acid in this product. And so you don't have to have two different feed pumps. So the next step is we want to filter jars. So I use 1 liter jars. These are very simple to use, very simple to clean. If you drop one, it's maybe $5 to $10 to replace versus the square jars that might be $200 to replace. And so there's no reason why you can't use 1 liter jars versus the 2 liter jars. Plus use half as much water as well. So it's, I just found, I used to use 2 liter jars for years and years, and one day I dropped a square jar and start using 1 liter jars, and I'll never go back to a 2 liter jar. So if the water's been sitting for a while, you want to mix it up a little bit in case you got suspended solids that have settled out. So, and so each of my jars, this is a 4-jar tester, and so I have 4 jars. I have labeled jars 1, and then jar 2, and so forth. So I'll just take this jar and dip it down here a couple times just to mix it up again. And then let me move this back here a little bit. I'll just fill it up. I'm not worried about whether I'm over if I have over a liter, I will dump some out. All right, now I'm just going to look at how much water I have for each one of these, and I'll just dump some back out. And I'll get a towel to help dry off the jars as well. Have plenty of towels. Everything's wet, so it's easy. The towels makes much easier to dry things off, keep things dry. So I'm gonna have at least a liter of water here. So I'm gonna put a little bit here, and we're gonna. You don't have to be exact, but get pretty close to it. So this has 1 liter water now, so this is jar 2. I'll just place this over here, and then just do each jar. Lift up your paddles, place each jar. These paddles have a lock, so you want to lower the paddle and then lock the screw in so the paddle doesn't slip when you turn on the jar tester. So I have my jars on here, and the next step I want to do is I'm going to put Post-it notes or some kind of label for each jar, what I'm going to be dosing, what chemical, and what my dose will be. Okay, so I've already done some jar testing the day before to kind of see what dose I need to be in. And so on this demonstration, I'm just going to do a kind of a wider range. Usually when I'm dosing, say if I'm doing 50, 40, 30, usually I go in increments of 5 milligrams per liter. So where I initially started was 35, then went 35, 40, 45, 50, and then the next set was 55, 60, 65, 70. Today we're going to go 50, 60, 70, 80. And this is going to be alum. So alum, it's going to be 50, 60, 70, and 80. We also, this is because this is a blend, a chemical that has also sulfuric acid, we're also adding sulfuric acid as well. And the sulfuric acid, to get the dose of this, and we'll go over the calculation on how to do that, but it's basically, we're going to take our dose of alum and we're going to multiply it by 0.1919. That will give us our sulfuric acid dose. And I need to get my calculator. And so 50 times 0.1919, that's a 9.6. And then for 60, this is going to be 11.5, and then for 70, 13. .4, And then for 80, it's going to 15.35. Also, before I begin, I have a notebook that I write down information for each jar, what I'm dosing, and all the analysis that we'll do later. Use the form. I found them that they can get in the way. I rather use a notebook. And so this is a kind of an example from yesterday when I was doing jar testing. Is I write down the jar number, how much alum I'm adding, how much sulfuric acid I'm adding, and then my analysis is just my filtrate into use, the UVT, UVA analysis, settled water turbidity, and percent UVA reduction. And I'll have this for each jar right here. And then I keep everything in a notebook so it's easy to go back and look at your notes and things like that versus using forms. I'll put down alum for jar 1, and we're doing 50 milligrams per liter, then H2SO4, we're going to be dosing 9.6. And usually I'm filling this out actually while it's during the jar testing process when I have some dead time, and I'll use that time to fill the form out, but in this case I'm doing it right now. For each jar I'm writing down, I'll write, like for example, I'm doing jar 3, I'm writing down the name of the chemical and what I'm dosing. And for jar 3 I'm dosing 70 milligrams per liter. Then for the sulfuric acid, that calculates to 13.4 milligrams per liter. And then the rest is the results of the analysis. So I'm writing down the filtrate, what the filtrate turbidity will be based on our filterability analysis. I'm writing down the UV transmittance value, percent transmittance. More importantly, what you call the UV absorption value. That's the indirect measurement of dissolved organics. We can't readily measure the DLC in the water, dissolved organic carbon, but we can measure simply UVA, which is a surrogate for DLC. It's a very important parameter for systems that have or any kind of organics in the water. And then we have settleability. We'll write down what the settled water turbidity will be from the jar testing. If you don't have settling, then that's a parameter you don't have to measure. And then the last one is just a percent UVA reduction. It's similar to think of reduction of DLC in the water. And so we write down, so this is the primary information I write down for each jar. If I'm doing a coagulant 8, I'll also write down what that dose is as well. What I'm going to flash mix at and how long. Usually it's the same. So the flash mixing, it's going to be at 200 RPMs for about 20 seconds. And then flocculation process. The flock mixing speed is going to be at, it can range from usually from 20 to 30 RPMs, depending on what kind of flocculation system that has. But either one, I'm going to use 30 on this one. So we're going to mix at 30 RPMs for 5 minutes. And that's it. So pretty much this all stays constant this is applied to just about most types of systems that you're working with. There's an exception if you're working with the active flow system, which the flux mix will be a little bit different, but the analysis will still be all the same. Okay. Now we have our syringes. These are used to pull the flocculated water for the filterability analysis. I have them marked as jars, 1 through 4, just to keep track of which is which. I'll put them up on the base of the jar tester. And then before we do our jar testing, we're going to prepare our filters. One of the important parameters in jar testing is the filterability analysis. We want to know what coagulant dose that gives us the best filtrate turbidity. that's one of the main goals in water treatment, is to make a good filtrate water for compliance. And so we have our filter holders, and I have these labels, 1 through 4 as well, to keep, make sure I don't get them, mixed up with the jars. And you take them apart, and I keep them loosely tight. When I store, they're just loosely on. You don't want to tighten them up when you store them, because you have a rubber O-ring that you don't want to squish, while it's in storage. And so this is our filter screen. So we'll take the tops off. And then we have our filter. So the filter we use is a 1.2 micron absolute or isopore membrane. It's absolute pore size membrane, and this is the membrane. This is the membrane you want to use for the filterability analysis. You don't want to use anything that's smaller or larger, and you don't want to use something that's called nominal size. You want to use something that's called absolute, and this is the filter that will provide the equivalent performance for what a media filter will do. It's a 1.2 micron isopore membrane. This is what you want to use. Use anything else, then you're not going to be able to distinguish between a strong flock and a weak flock. If you have a weak flock, this will go through the filter and show up as turbidity. If you have a strong flock, it will be removed. If you use a filter membrane that's smaller pore size than this, then it's going to remove both weak and strong flock, and you're not going to be able to distinguish between weak and strong flocks between jars. And if you use a membrane filter that's larger than 1.2 micron, like a 2 micron filter, then it's going to allow weak and strong flock to go through, and you're not going to be able to distinguish between a strong and a weak flock. So before you put the filters on, if I was trying to put a filter on here, it would just kind of slide off, and these filters membranes are separated by a blue paper. And to properly put these on, to make it easy, the first thing you want to do is wet the filter screen. And so what I'll do is I'll take DI water and just wet each filter quickly. And this is so the membrane will stick to it pretty easily. And so if you see a blue paper, and below that is a membrane. It's a shiny, that shiny membrane that looks like that. And what I'll do, I'll just hold this filter screen, and I'll just lay it over like this, and just leave it like that, and that paper will pop off like that. Just like that. If you don't wet it, the paper will just stay on there like that and won't pop off. And so and you want to center the membrane, so you see it's off to the side like that. You can tell if you just put your finger like that, and you can flick it, you can see that. And so sometimes you can move it over with your finger. If it doesn't, you can take this paper right here and slide it over just a little bit like that and center it, and put your finger right here to hold it down and pop it off, and then it's center. And then you could take the other part of the membrane, you just put this on. And this is for jar 1. I'll just put this in front of jar 1. And you do each membrane. So here's the shiny part. Here's the paper on the top. So slide it over, and I'll use my finger to try to center it like that. And just let that pop off like that, and I'll do the other membranes. And I'll come back to them and center them up. So here's the shiny part of the shiny membrane. Here's the paper form. And if I were to move that paper, this one has 2 pieces of paper in front of it. Let's see let me move that one out. So the membrane, the paper kind of sticks to the membrane, but you can see here's what the membrane actually looks like. So this is not the membrane. Some people might, if they're doing this for the first time, they might think this is the membrane, but it's not. It's just the paper that separates the membranes. And so you just stick this membrane on. Usually, you're going to have the paper on top. And then we'll do the next one. the last one. So part of the hardest part of doing this is trying to get the paper filter out of this box here, and then that paper will pop off like it is right now. And then we'll look at it and see if it's center. Sometimes you can move it with your fingers, you know, if you move it on the edge here, like that. That's pretty center. And then we'll take this other piece of the filter holder and screw it on. And then this is jar 4. And then this is to the side here. And you can tell it's off center just because I can move the membrane up just by moving my finger on the side. And now it's center. Usually, this is dry because it's dry. Because it's dry, a lot of times the O-ring will pop out if you're trying to stick it on this way. It'll just come out like that, and you'll put it on. So if I do that, it comes out. If I was trying to screw it on, so what I will do is, so by wetting the filter screen, the membrane will stick to it, and I'm going to center this again. It's not center, or they didn't center it yet, so now it's center. By moving my finger around, I can tell it's not hanging off to the side because the membrane's not coming up anymore. And so what I'll do is, instead of tilting this over like this, I'll just tilt this over because the membrane is now, sticking to the filter screen. And then I'll just screw it on like this, and you're done. We're going to be using 2 instruments. We have our turbidity instrument, and that's going to be used for measuring the filtrate turbidity. And if we have settling, if we're working with a plant that has settled, then we'll do settled water turbidity as well. The other important parameter, which is very important data, is our UVA instrument. And this measures the UV absorption of the water. It's a surrogate for measuring the dissolved organics in the water. So you can think of measuring DLC in the filtrate water. And one of the things I do before I do the jar testing, I actually measure the source water turbidity, the source water UVA, UVT. But because we want to measure also, we want to measure the dissolved organics in the water. We want to take the source water and run it through a filter. And the filter that we run it through is a 0.4 micron absolute membrane. So this is a tighter membrane. And what it does is to remove most of the suspended solids so that we're measuring only the dissolved portion of the water, which is going to be the UVA and UVT. And so we want to compare the UVA absorption of the source water to that of the filtrate water. So we kind of get an idea how much we have in the source water and how much we're removing and what's coming out of the filter as well. So all that was done earlier. Make sure your instruments are calibrated. This is calibrated. You usually calibrate these every once a month or every 3 months, according to the manufacturer. This I'll calibrate once every day. Anytime I use it, if I'm using it wherever day I'm using it, I'll calibrate. It's very simple. You could just use DI water or organic-free water, and it's very simple to calibrate. And so when doing jar testing, you got to have both these instruments. If you're just doing turbidity, you don't have this, then you're blind. You don't know if how much organics you're removing, because you can get good filterability at a lower dose, but you may not be removing much organics. And so you need the purpose of the jar test is to determine what coagulant and dose or any other oxidants that you might be using that provides the best, not only filterability, but organic reduction as well. And also looking at settleability as well. So we're looking at all 3 parameters. So before we begin, we want to turn on the jar tester, and we'll go up to about 200 RPM just to make sure everything is center. And I'm just kind of looking at the jar to make sure they're centered and there's no slippage of the paddle. Make sure it's tight. And then I'll bring it to a lower speed. And so I have a low speed, and this is when I'm going to add my coagulant. So when we made up our stock solution, I used this pipette. I don't want to use it for the jar test because it may have high residual of the product, and that could cause me adding more chemical than I want to be adding. So I'm just going to throw that away and use a new pipette. So this is a 2% solution. So I'm dosing 50, 60, 70, 80. That means my mils per, how many milliliters I'm going to add to get 50 is going to be 2.5. For 50, for 60 it's going to be 3. For 70 it's going to be 3.5, and for 80 it's going to be 4, because it's a 2% solution. So I'm going to set my pipette to 2.5. And then I'm going to take a little beaker like this. Let me make sure this is well mixed again. Once you got it mixed, it should be fine, and this will last. You know, people ask, like, can I use, if I'm jar testing the next day, can I use the same stock solution? It should be fine for a few days. But, you know, after 3 or 4 days, I would make up a new stock solution if you still have some, you know, left over. So I have my phone as a timer, and for the first flash mix, we're going to go for 20 seconds. I'll just count to myself. Whether you flash mix for 20 seconds, 30 seconds, for a minute, it doesn't matter. 20 seconds is all you need. But if you went a minute, it's not going to make any. It's not going to impact your results. So 20 seconds is enough. If you go a minute, that's fine, but you're just wasting another 40 seconds. So you don't really need to go a minute. And 200 RPMs is plenty of energy to properly disperse the coagulant. All right, so first of all, I just ran at a low flocculation speed, about, you know, close to 30 RPMs. And I'm going to start with my pipette. I'm turning this to 3 now for the second jar. Gives me a 60. Then 3.5 for jar 3. That is 70 milligrams per liter for alum. And then 4, pipette changed the settings to 4 mils to give me a dose of 80. And then I'll flip it up. About 200, and we'll just count to 20. And then I'll start my clock. And basically we're going to flock for about, 5 minutes. You may ask why we only flock for 5 minutes and maybe 20 minutes, like maybe what you were taught. Well, the flocculation, basically in a full-scale plant, they're flocculating for 20, 30 minutes to develop a flock to get the best settleability that they can, to settle out as much suspended solids as they can before the filtration process. This is not required, this is not necessary for jar testing. All we're trying to do is make a flock so we can analyze the filterability of that flock, whether that's a strong flock or a weak flock, and look at the organic reduction. Whether you flock for 5 minutes or 20 minutes, it does not, or 30 minutes or even 40 minutes, it does not impact the filterability or the organic reduction. So we can get away with just flocking 5 minutes. The settability is all relative between each jar. Whether the longer you flock, the better, to a point of diminishing return, the better settability you're going to get, but it's still going to be relative between each jar. So there's no reason to flock for 20 minutes because you're just wasting another 15 minutes in the jar testing. And especially when, you know, you got a change in water characteristics going on, you got maybe a storm event, and you need to do some jar testing. You don't want to be spending several hours jar testing. You want to be able to do a jar test within, you know, a reasonable time so you can make full-scale plant changes, you know, within an hour. So if you don't have, there's lots of plants out there that don't have settling. You have your roughing filter, you have plants that have a roughing filter. You have direct filtration plants that don't have settling. They're missing that stage. You don't care about the settleability then, and you can just skip that part. So we'll flock for 5 minutes, and then after the 5 minutes, we'll pull the paddles out, and we'll let it sit there for 5 minutes, let some of the flock settle out, but not all of it. And we'll draw some of that flocculated water to do the filterability analysis. If you're working with a plant that doesn't have settling, then after 5 minutes, we'll pull the paddles out, and then we'll draw our samples immediately afterwards. Whether you do it immediately or wait 5 minutes, it's about this, the end results are still going to be about the same. The only reason we wait 5 minutes for a conventional plant, because usually we have a lot of flock, and we don't want to plug up the filter. We don't want to overwhelm the filter with all the flock. We're still getting enough flock after 5 minutes. But if you did it right after the end of the flocculation process, some waters, they have a lot of suspended solids. They can plug up your filter if you don't wait at least 5 minutes. Now, some people like to look at the flock size and this and that, but you can't tell by looking at the flock size and how well something settles. There's no supporting data as far as how well, if some of that flock went into the filter, how well it's going to filter out and what the organic reduction is. So the old school is that they're looking at the jar that gives you the best settleability, but there's many plants out there, but that doesn't give you the supporting data on the filterability and organic reduction. And then if you have plants that don't have settling, then what do you look at? So settleability is one. One of the things with settleability is that you can look at different coagulants that gives you maybe the same filterability, organic reduction, but maybe maybe coagulant B gives you better settleability, and then that's where you can start comparing different coagulants as far as which one gives you the settleability when they both perform the same in regards to filterability and organic reduction. So I have cuvettes. These are 1 through 4, and these are used for the settleability analysis. And one thing I would say is that I keep DI water in the cuvettes to keep them from spotting and keeps them clean. So that's for storage. So that's one thing you might want to do with your cuvettes. And then I have a cuvette that I use just only for the filterability analysis. I call it F2. They have a F1 and F2. These are only for the filterability analysis. And so it's my cleanest cuvette. So I have 5 minutes. It's already elapsed. So I'm going to reset the clock and turn this off. Lift the paddles up. And normally I'll take a picture of this, what it looks like at the end of the flock period. And as you can see, there's a lot of flock in each jar, and we'll give it 5 minutes for some of it to settle out. And I'm gonna dump these out, so I don't have to do them later. So I'm just dumping out the DI water. And then your filter for the cuvette you're going to use for the filterability analysis, you want to make sure you use a very clean cuvette. And one of the ways to tell is that you get some clean bottled water, and you can measure what the turbidity of that is. And so I'm going to look at this real quick to see where I am on the turbidity. It should be I would like to see like a 0.05. That tells me that's a good cuvette. So it reads 0.04. So that's cuvette. That's good. This instrument, the limitation on the instrument is about 0.04. That's about the lowest you're going to read on this type of turbidity instrument. So that's a very good reading. So that means my cuvette is clean. I don't have to worry about cleaning it out or anything. So I use the same cuvette for all my filterability analysis. I don't use different cuvettes. Rinse out. Now, a lot of times, you know, sometimes your best jar is the one that has the best settling, but which is fine, but you still got to do the filterability and the UVA analysis. You know, you could have maybe this jar is the best, maybe this jar has a better settleability than this one, but this might be your best jar. So we'll wait, like I said, we'll wait about 5 minutes, and you'll still have plenty of flock to pull out. And when we're doing when we do this, we'll use these syringes. They're 30 ml syringes. They have a rubber. I'm not sure what this is called, but it's a rubber end on here. And don't get the plastic ones; those are hard to work with. And basically, we're going to pull about 20 mils. And what I'll do is I'll stick it in the beaker, and I'll just count to 10 until I get about slowly count to 10, and I'll syringe about 20 mils about this quick. And whatever rate you do, just keep consistent for each jar. But I don't go like this really fast. You know, do it in a slow rate of just count like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then go on to the next jar. Now on this one we add alum. Now if you're doing a coagulant aid, after we say you want to do a coagulant aid as well, I would have another stock solution prepared. And so once you add your primary coagulant, then you go back and do the same thing for your coagulant aid. So you do your primary coagulant first, then add your coagulant aid, and then you flash mix. If you're doing like a pre-oxidant, like potassium permanganate, and you want to like see what impact potassium permanganate has on the flocculation process and filterability and organic reduction, then what you would do is you make up your stock solution for the potassium permanganate, and you just add the potassium permanganate first, and you flock at a slow speed, maybe 20 RPMs. And you may go, depending on what detention time you'll have out in the system, if you have an hour detention time before you add your flock, then you just flock for an hour, and to get the full oxidation of the potassium permanganate. And you dose at different different doses for the potassium permanganate. And then once that's all done, then you start your regular jar testing process. So we're getting close to 5 minutes. So we can start now drawing our sample. All right, so we draw our sample. So now the rest is just analysis. We're done. Our jar test has been done. The jar testing itself is 5.5 minutes. So we take our filter holder and we're going to attach it to our lure lock syringe. This is a lure lock, and we'll just take it like this and just screw it on like that, snug. And so we're going to filter into this cuvette right here. This is our clean cuvette. And the first thing we want to do is we want to filter the waste a little bit of the membrane, just to make sure there's no dirt on the membrane. And we're going to go at a drip rate. So we never go at a steady stream when we're filtering, we're just at a drip. So we're going to filter the waste about 2 to 3 mils, and then we're going to go directly into the cuvette right here. And it's just a drip rate. And use your thumb to push down the syringe, and as you fill up the cuvette, you're not going to fill it up all the way. I usually go just below these numbers right here. You may start feeling some head loss. That's fine. Don't try to keep the same drip rate. You can slow, it'll slow down. That's fine as well. And usually it's about 60 seconds to 90 seconds to get a sample. And yeah, plenty of time. So that's it. And then I'll put my lid on here. And then we want to wipe it down with a dry towel, any water that might be on here. Now because we're filtering through a membrane, sometimes you might get microbubbles on here that can cause a artificial high turbidity. So you want to move the cuvette around like this to remove any microbubbles. This is a cloth that comes with a turbidity meter. You can wipe it down. And then our first analysis is doing a turbidity. Now you want to do several readings to make sure that it's stabilized. Sometimes you'll get a high readings and then all of a sudden it'll go down to the value that's looking for. So this is the 0.06, which is about what I expected. 0.06 again. And then if you think you might be able to read lower, we could put some silicone oil on the cuvette. That's 0.06. So I would write that, if I didn't do anything else, I would just write that number down, 0.06. But I'm going to see if I can go a little bit lower, and I'll just put a couple drops of silicone oil on the glassware, so it helps remove any kind of scratches or anything like that that might be on the cuvette. Wipe it off, and I'll look in the light and make sure there's nothing smeared on the glassware. And I'll do another reading. Still 0.06. So I'm going to write down 0.06. The first thing you want to do is I want to calibrate this instrument before we start our analysis. And we use DI water or use organic free water. And so this is very simple. There's a button that says calibrate. You click that on, you push that down, you just insert your cuvette, and now it's calibrated. Simple as that. And so now I'm going to take this, dump it out, and then this is I'm transferring my filtrate water into this cuvette. So we're going to read the percent UVT on this, and then the UVA. So we just insert the cuvette, and it reads 90.1%, and then we're going to toggle to the UVA value, which is 0.045. On the cuvette, I'm going to dump this out and just kind of rinse it out with some DI water before I do my next analysis. I don't care if I get too much water, just rinse it out, and then the lid, some DI water, and then I'll start again with the next filter was jar number 2. I'll put on the filter for jar 2. I'll waste 2 to 3 filter to waste, about 2 to 3 mils. And then I'll go directly into the cuvette. And just at a drip rate. It could be a slow, fast drip rate, but as long as it's the drip rate, you're fine. Okay, that's enough. And then put the lid back on, dry it off. Again, you want to, because there's a membrane filter we're going through, we want to make sure there's no microbubbles that within the water that will cause an artificial high turbidity. Okay, and then let me wipe it off a little bit with this cloth. Okay. And again, we're going to take several readings. This is again 0.06. .06. 0.05. That's 0.05 again. I'll do one more. So 0.05. Take it out, put that lid back on, and then we'll dump this out and transfer the water into here. And we'll measure the UVA, UVT value. Now I expect, because this is a higher dose, that the UVA value will come down, meaning that there's less organics in the water. So the last one was 0.045. This is 0.041. So in systems that have disinfection byproduct issues, let me toggle to get the UVT. The systems that have disinfected byproducts, you want to have the lowest UV value you can, and usually if you have something that's 0.03 or less, then you have less of an issue with disinfection byproducts. Now this is in the 0.04, so my guess is that the system would have disinfectant byproducts just based on the UVA value. I'm going to rinse this out, and then I'll let that sit in here. So you got a good turbidity value, but the organics are not that great. So we're still looking for the dose that provides the best organic reduction to the point of diminishing return. So I'll take my cuvette again, I'll rinse it out with some bottled water, just to make sure it's clean for the next sample. All right, and then I'll take jar number 3, filter the waste, a couple mils. Now if you get to a point where it's just so hard you can't, because of the head loss, you don't have to fill it up as much. Just stop. Can't really push any more water through it. It's a very slow drip. So we're going to wipe this off, the water off, and then so just know, for those that are new, there's an arrow in front of this cuvette. This points forward, lines up with this arrow on the instrument. So that's 0.05 off the bat. That's 0.05. I'm going to add a couple drops of silicone oil just to see if we get it down to 0.04 or not. And I'm going to look at this, make sure it has nothing smeared or from the oil, and then we'll put it back in. So let's do one more here, 0.05, 0.05. So again, this is about the same readings as the last 2 readings. So the main thing we're trying to do is, are we improving on organic reduction? So we'll see. And so the UVT on this is 90.9. I expect that to be 91 something. So this is a dose of 70 of alum. So it's 91.2, better than the previous jar, which is expected, and 0.039. Okay. We'll rinse this out again. Okay, now we'll do our final jar. Okay, we're going to remember filter the waste, 2 or 3 mils. And then we're going to get our cuvette. and then just go right directly into the cuvette. And just be patient, the drip rate. And by the time we're done with all this, almost 25 minutes will have elapsed at the end of the flocculation period, and that's when we do our settleability analysis. So there's no rush trying to get this through, and people may ask, well, why 25 minutes? Well, because it takes about 25 minutes to do, from the end of the flocculation, to do all the analysis. You can go longer if you want, but then you're just kind of wasting time. So again, settleability, it's just relative between each jar, whether you settle for 10 minutes, 15 minutes, 20, 25, or 30, it doesn't matter. All right, so I'm gonna remember to always tilt the cuvette, make sure you remove any kind of micro bubbles, give it a good wipe, and then let's do a reading. .05. I'm going to put some oil on here again. So when you're wiping, use the velvet part when you're wiping, not the backing of this cloth. So this is reading about, look like it's going to be 0.05. Okay, now it's 0.04. Let's see if we can get a couple more numbers like that. 0.05. So I'm going to use 0.05. Okay. So this is 0.034 and 92.3%. All right. So let's rinse this out. So it's a better, same turbidity, but a little bit better organic reduction. We have about 24 minutes elapsed, which close to almost 25 minutes. So what I will do is I'm going to slowly move these jars out so I can take a sample for the settleability analysis. And so that's where the 25 minutes comes about, is that because by the time I'm done with the analysis, almost 25 minutes has elapsed, so you're not wasting time. So you want to be as efficient as you can with jar testing. So almost 25 minutes to elapse, so we can start doing our settleability. And so basically I'm just going to do a quick dip, one dip, you don't do it twice, just do one quick dip like this, about an inch or two below the surface of the water. Okay. All right, so the next step is to read see what the settleability is for each jar. And what I'll do, I'll take 3 readings and take the midpoint for each cuvette, for each jar. So I'll start with jar 1. I'll take a read, and what I'm doing now, I'm drying the cuvettes off. 1.72. 1.77. So it's 1.77. That's the midpoint. And then I'll do jar 2. .57. 1.72. 1.66, and that's their midpoint. .71. 1.72. 1.72. And then the last jar. .17. 1.11. 1.7 is the midpoint. Okay, 1.19. All right, so we're done with analysis. And so like I said, 27, since the end of the jar testing, 27.5 minutes have elapsed, and we had 5.5 minutes of jar testing. So that was quite a little bit less than 35 minutes to complete the jar testing and all the analysis. So what we have here, we have 4 jars that had almost basically the same filterability. And so what else do you look at? Well, we want to look at organic reduction. And so we have a dose of 50, 60, 70, 80 of alum. And so the organic reduction improved for each dose. So the UVA for the first jar was 0.045, and then our last jar was 0.034. That's a big difference between 0.045 and 0.34 as far in regards to potential disinfection byproducts. And as I said, you want to get, if you get something that's below 0.03 UVA, then there's less of issues with disinfection byproducts. Doesn't mean you're not going to have them, but as far as being over the MCL, there's less of a chance of being over the MCL, but still, you can still be over the MCL depending on the water age that's out in the distribution system. So if I wanted to do more jar testing, I would probably look at a higher dose. Maybe I'll go, look at 80 again and 85, 90, 95. Now, from what I've done already, I did go up to 90, and after 80, there was no improvement as far as UVA reduction. The filterability was the same. We're getting 0.04, 0.05, but there was no improvement with organic reduction. So 80 was our cutoff point. 80 is like our diminishing return value. And so that would be the number, that would be the dose I would recommend the plant would, dose at for optimize as far as filterability and organic reduction. And on this case, the settleability was also the best for jar 4 as well. We have settleability of 1.17, and all the other ones were around close to 0.17. But, what is that? The settleability says, how well something's going to settle. It doesn't have any other information besides that. There's nothing that says, well, this is also going to be your best filterability. This is going to give you the jar that gives you the best filterability and organic reduction. There's nothing, no supporting data on that. And again, if you have a plant that doesn't have settling, then you don't care about settling. You don't even need to do the settleability analysis. You're just mainly looking at filterability and organic reduction. So there are coagulants that, if you're really looking at something that wants to give you, if you have a coagulant you're using that's not giving a very good, giving good filterability and organic reduction, but your settleability is not very good, then you can test other coagulants. You can look at coagulants that settle out pretty fast. They react, they're fast reacting, they settle out quicker. But every water is different. So some of them, sometimes these coagulants work well, sometimes they don't work so well. They may work well for water A, but then a different water source, it may not work at all. So you have to, by doing jar testing, you can see which one, by doing jar testing, you can test out as many coagulants you want and also look at coagulant aids. For this particular water, we're getting good filterability, from 50 to 80. But let's say the filterability wasn't that good. So what do? Then we start looking at maybe a filter aid that will help strengthen that flock, make it more stickier. And these are like polyamines or polydiatomax polymers that you can use. You use at a much lower dose. And then what you would do is you take a jar, maybe one of your jars that you think is pretty good, but doesn't have very good filterability, and you'll just you'll start with a jar of, let's say for example, 60 without any polymer. Then you do another jar of 60, and you start with a low dose of a polymer, and then you go up, and then your third jar you do 60, but with a little bit higher dose of polymer, and then the same thing with the last jar. So you start looking at a range of different polymer dose and see if that helps with the filterability. That's how with jar testing, without doing full-scale, pilot testing, you can do all this work just doing jar testing. And the results we get from here are transferable to full-scale operations. So if I just say, if I told the operator, okay, you need to go to 80, they will get, the 80 will provide the same filterability results or better. The plant, usually if I'm getting 0.05, they'll get at least that or better in the full-scale operations. And the same thing with the organic reduction, the UVA value. Whatever UVA value I'm getting, they're going to get at least that or better. So the filterability analysis is meant to model, simulate what a media filter will do in a full-scale plant. So many times, for this example, we just happen to have good filterability for all 4 jars, but many times in jar testing, the filterabilities are pretty poor, and all of a sudden you have good filterability. So that just means that you're just underdosing with the coagulant, and then until you get to the right dose is when you're going to get good filterability. Assuming that the flock, you got a good, strong flock. Sometimes, like I said earlier, the coagulant you're using does not produce a strong flock, and that means you have to add some kind of flock aid or like a polymer to strengthen that flock, make it stickier so it stays on the filter longer. But in this case, we just, we got good filterability. Now at the lower dose, I did the lower dose, and one of the things that helps me to start with, the starting point, is that I use what we call a laboratory charge analyzer. And you don't see it here, but what we do with it is that it measures the negative charge of the water, and it'll automatically dose the coagulant until that charge becomes neutral. And that's my starting point. So once the charge becomes neutral, for example, and then I'll start jar testing around that. Now, just because it says, for example, say the LCA, the laboratory charge analyzer, said it takes 40 milligrams per liter of alum to neutralize the charge, that doesn't mean you're going to get good filterability or organic reduction. You might have good filterability, but but the organic reduction is not very good, and that means you have to add more. You want to optimize for the organic reduction as well, so that means you have to add more coagulant. And as I said before, there is a point of diminishing returns where you can keep adding coagulant, higher dose, and you're not going to improve on organic reduction. So, and that's how you determine that with jar testing, is to see what dose gives you the best filterability, but also the best organic reduction, to a point of diminishing returns where you're not going to improve anymore. And then and there's a point where you start to overdose, then the filterability could start to decline, and you start to get breakthrough of flock, and the turbidity will start to spike up again, and the UVA value starts to go up as well. Okay. So there is a point where you can be underdosing, overdosing, it'll show up. It can show up in the filterability and UVA analysis. But every water is different. There's, wherever you work, what kind of results you get on one water, you may get totally different results for another water using the same type of coagulant and so forth. So it's all, somebody may ask, well, how does this coagulant work? Well, you have to jar test it before you know how well that coagulant's going to work. You can't just say, because it worked on this water over here, it's going to work really good on this other water. You have to jar test. Remember, there are at least 3 operating performance goals in surface water treatment. They include filterability, dissolved organic carbon reduction, and settleability. Jar testing can be used to determine the best coagulant and dose for meeting all 3 treatment performance goals. However, most operators and engineers were taught only to evaluate floc settleability and not consider the strength of the floc for filterability and dissolved organic carbon reduction. Jar testing procedures and analysis presented in this video addresses all 3 performance goals that provides the supporting data needed for operators and engineers in selecting the best coagulant and dose for overall full-scale plant optimizations. Before we do jar tests, we really want to know what's our baseline is as far as what's in the source. So for what I will measure is the source water pH, what the turbidity is. So the source water pH was 7.9. The turbidity is just over 9 NTUs. And then also measure alkalinity. Alkalinity is important because we want to know whether you, especially if you don't know what source you're working with, you've never worked with a particular source, you want to know whether it has a very low alkalinity, because that will limit what kind of give you the direction, what type of coagulant you want to use that has, there's coagulant that has its own what we call basicity, where it doesn't it doesn't reduce your alkalinity of the water very much. Where if you're using alum, for every part of alum you use, it reduces alkalinity by 1/2 part of calcium carbonate. So this particular water has 81 milligrams per liter of calcium carbonate, and then I'll measure the UVT UVA just to see what it is. And you look at this, the UVT was 63.7%, UVA 0.195. Now we want to compare, when we're looking at filterability UVA, we want to compare dissolve versus dissolve. So that's the surrogate for DLC. And so we run that source water through I'll use a syringe, just like this right here, but I'll use instead of the 1.2 micron absolute isopore membrane for the filterability, we'll use a 0.4 micron filter here, so mainly to remove most of the suspended solids. So I'll run it through a membrane. I'll measure the turbidity again just to see what the turbidity is. It was 0.42. And then I'll measure what the UVT and UVA. And there is a big difference between after you remove the suspended solids, that the UVA is 0.139. And this is what we're going to compare with the filterability, with the filtrate UVA. We want to compare what's in the source water in the dissolved form and compare that with the filtrate UVA. And then the post-filter, this is from the plant. So this is a sample taken from the plant. So I want to kind of see what they're operating at. And so the turbidity I got from the plant was 0.07. The UVT, 92.3%, and UVA was 0.034. And this is what our last jar was, the 80. Now I suspect this plant will do a little bit better. This particular plant was dosing, it's not in this paper, it was dosing about 60 milligrams per liter of alum. And we show that 80 is where they need to be as far as the optimized organic reduction. So I suspect this number to be a little bit better. And then post-chlorine, this is just what the turbidity after chlorination, and then the UVT, UVA. Now, when you're comparing UVA, you don't want to, the reason I took this sample is because when chlorine reacts with organics, you make disinfectant byproducts. And when you do that, it reduces the UVA value. So if you're looking at your UVA value, you want to look at the post-filter before any kind of chlorine to see what the actual UVA is. Once you add chlorine to it, some of that organics some of the dissolved organics that wasn't removed in the treatment in the treatment process gets reacted with the chlorine, and it reduces that UVA value, thinking that you have less organics in the water than you actually have. So if you look, the UVA went from 0.034 to 0.026. This is because you had some chlorine that reacted with the organics. So I do this just to kind of show what kind of reaction that we're getting from the chlorine system. So you can take this value right here, this UVA value, I can add chlorine to it, and I can reduce this UVA value, and you would think that you have less organics, but what you did is that you just reacted, you just made disinfectant byproducts, and so some of that organic converted to disinfectant byproducts, and so this UVA would be reduced down, the value would decrease. So what we're going to do for the UVA reduction, percent UVA reduction, we'll take this 0.139, and we'll take our, let me find my data sheet. I think this is it here. We'll take this, and then we'll calculate the percent UVA based on each jar. So that value was 0.139 UVA, and that was our filtrate source water. So basically what I will do is just take the 0.139 minus the 0.045, then divide that number by 0.139 times 100%, and that gives me 67.6% reduction in UVA, or you can think of it as reduction in DOC. And then I'll do the same thing for each one. 0.139 minus 0.041 equals divided by 0.139, and that gives me 70.5% reduction. And then we've got a 0.139 minus 0.039. 139, that gives me about 71.9% reduction. And then the last value is 0.139 minus 0.034 divided by 0.139, and that gives me 75.5%. Now, this seemed like a high number, which is fine, but think about what you're really looking at. What really matters is what the actual UVA value is. Same thing as DOC in the treated water. You may have, your DOC in the source water might be 10 milligrams per liter, and coming out might be 5, and you got a 50% reduction. But 5 is still very high. Even though you got 50% reduction, you say, hey, I got 50% reduction. Well, you still got a lot of organics coming out. You really want to have, you really want to be looking at this number. This is fine. This tells you like you're actually removing organics in the water, but the number that you're really going to focus on is what the results of the UVA values for each of the jars, of the filterability analysis. So again, this is my data sheet that I use, that I fill out by hand. And we start with jar 1, and we have a dose of 50 milligrams per liter of alum, and that calculates to 9.6 milligrams per liter of sulfuric acid. And the way I got that number, and I'll write it down over here, before we jar test it, we made a 2% stock solution for alum. And this is based on the product we use is called 7% acid alum, meaning that it has 7% sulfuric acid and 36.48% alum. So I wanted to make a stock solution just based on alum, and so I made a 2% stock solution just on alum. Now, how do we calculate what percent is the sulfuric acid? And the way you do that is that you just take the 7% of sulfuric acid, divide that by the alum, strength in the product, which is 36.48. And we're going to times that by the stock solution, which is 2%. And when we do that calculation, we're going to go 7 divided by 36.48 times 2. And then our stock solution for sulfuric acid is it's actually 0.38, say 4 or 384, not 384% H2SO4. So now, when I add my when I'm adding my so let's say I'm adding, for earlier when we did our Joe, this is 2%, so these are 1 liter jars. So if I want to dose 50 milligrams per liter of alum, I'm going to add 2.5 mils of stock solution. If it was 1%, I would just add 5 mils times 10. That gives me my dose. But because it's 2%, I'm going to do half as much. That's 2.5 mils that I added. So to calculate how I came up with 9.6 milligrams per liter of sulfuric acid for 50 dose, it's basically, I'm just going to do it here, you just take the 2.5 mils times the percent strength, which is 0.384, and you're going to times that by 10, and that's going to give us times 2.5 times 10. That gives you 9.59 or say 9.6. So we're just doing a ratio of the 7% sulfuric acid divided by the alum percent that's in this product right here, which is 36.48%, times our stock solution percent, and that gives us the what the actual percent strength is of the sulfuric acid in this stock solution. And now we know, now we can calculate the our sulfuric acid dose. And we do that for each one, and so like on this one, we added 3 mils of stock solution to get 60. So 3 times this percent strength for sulfuric acid times 10 will give you 11.5 and so forth. So this is a little bit tricky because we do have a blended, we have alum that's blended with sulfuric acid. Now with other products that are like ACH, aluminum chlorohydrate, that have maybe some other polymer that's blended in there, they're called blended, polymers. What we do, we're not going to try to break out the active ingredients. It's best to just assume 100% product when we're calculating our dose. And when we say dose, we'll say we're dosing as product. So like for example, let's say I had a product called 9800, or for example, say 9890. That might be a blend of ACH and some kind of polymer, polyamine. So the way we would, when we're doing our dosing, we might say we're dosing, say, 30 milligrams per liter of 9890. I don't care whether, I'm not concerned about if this is 40% and this is 10%, and then the rest, say 50% water. I'm not concerned that, because there's so many blends out there, it makes it difficult to try to break these out, and many times you don't know what the different concentrations are. So it's best to, except for the exception for alum and ferric chloride, everything else we'll just assume 100%. We're dosing as product. And so when we're doing our stock solution, for example, let's say I have a 9890 that has a specific gravity of 1.32, and we're going to assume 100% product. And I want to make up a 1% solution, stock solution. So I would use my equation. Remember, that's 1.32 times, say, 100. It's 100% product, and we're going to try to figure out how many mils to add. Say we're going to do a 200 mil stock solution, and we're assuming specific gravity 1, and we want a, say, a 1% solution. So X milliliter is just basically 200 divided by 1.32, and that will, and divided by 100 as well. So that's basically 2 over 1.32, and that's equal to about 1.49, I think. And we can calculate that out. Or it's actually about 1.5. And so that just said, so in the alum, we want to dose as alum, but everything else, just assume 100%. So in alum we had 36.48%, but for everything else we're just assume 100% for like the polymers and everything else, and it makes it much easier to calculate. And so when you dose, when you report your dosing, you might say I'm doing 30 milligrams per liter as 9890. You're not going to break it down to like, well, some of it's ACH, some of it is polyamine. We're not going to do that. We're just going to break it down as product, and that's the easiest way to do it, because there's hundreds and hundreds of coagulants out there, and polymers and things like that, and it's just easier to say dose as the product name. When I started the jar test, I started at a low dose just to see, what kind of results we get at the lower dose, and see what kind of improvements we get as we increase the coagulant dose. So again, we're doing an acid alum, so when we dose alum, we're getting some kind of dose for the sulfuric acid as well. So the first set of jars was, we started with the alum dose of 35, 40, 45, and 50. And so the analysis is that we look at the filterability, UVA, and settleability. And if you look at the first dose, we got a 0.1. The goal you should have when you're doing jar testing is try to get something that's under 0.1 into use. So the UVA is 0.055, which is it's not a good number. If you look at the UVT, it's 87.9%. So this is not a good, we're getting 60% UVA reduction, but still we have a high UVA value. We want to have this UVA value as low as practical. The settleability is a little high, 3.66 NTUs. And then at 40, still about 0.11 NTUs, a little bit of improvement on the UVA values, and settleability improved a little bit as well. And then we went to 45, and the turbidity was still kind of went up, shot up a little bit, 0.18. Not good. So this tells me, we're not in the right, dose range yet, but I started low on purpose just to kind of show that, when you're underdosing, you don't get, the results are not as good as when you're at the right dose. The UVA did improve a little bit, so we went from 0.055 to 0.49 on the third jar. Settleability still up in the 2s, and then jar 4 we did 50, and now 50. Now we dropped down to 0.06. Now this is our best filterability jar with the best filtrate turbidity of these 4 dosages. UVA is down to 0.42. Settleability improved quite a bit to 1.47. So now we're making progress, and now the next, so we're going to do another set of jars, and we're going to still increase the dose. So I got 50 here, and then I went to the next set of jars, and I went 55, 60, 65, 70. All right, so now we're due to 55, filterability, 0.07. UVA improved a little bit, 0.041. Settleability, below 2. And then we went to jar 7. and we're still slowly improving our organic reduction. So the main thing is that you don't want to like say, oh, we got good filterability. For example, like if you're doing just one set of, if you just did one set of jars, you say, oh, we got great filterability, but we don't have good organic reduction. And we want to find what dose that gives, that can improve this value to the point where you don't have any more improvements. So we don't just stop at 50, we keep on going. So we still get a little bit better improvement with the higher dose. We go to 60, 0.39, 65. Now we're getting better filterability, 0.05. We get 0.037 UVA value. And then 70, we get down to 0.35, 0.035, filterability 0.05. So we have much better performance at 70. Settleability still in the high ones. And then we do another set. So this is set number 2. And then we're going to do another set of jars at a higher dose. So we're going from 70. Now the next set we're going to start at 75, 80, 85, 90. So here the filterability 0.04. I miswrote this, so it's 0.04. And then the UVA is 0.034. That's 75. And then settleability 0.155. And then we go to 80. The filterability is 0.08. So it went up a little bit on that one, but the UVA went 0.032. And then the next dose was 0.85, was 0.04 for turbidity, 0.032. So it didn't improve on, so now I can see that it had no improvement from 80 to 85 as far as UVA or organic reduction. And same thing at 90, 0.04 and 0.032, still the same numbers. Even though this is 0.08, I decided to use 80 again to see as my max dose that's going to give me the best UVA. So what I did is I looked at 80 again, and I did 80 again, and then this time I got 0.04, and the same thing as UVA is 0.032. Now what I did on this set is that I wanted to look at a polymer, like a coagulant aid, or we call it coagulant aid or filter aid. I wanted to see if it had any kind of impact on the performance, any kind of negative or positive impact on the performance of this water. So I did one jar without it and got 0.04 and 0.032 for the UVA. Settability, about 0.142. And then I added 80 again, and I added 0.2 of this product called 8170. Same filterability, same. The UVA is slightly not as good. And then I did 80 again, a little higher dose of the 8170, 0.25. UVA, 0.033. It's really not much of a difference between 0.032 and 0.033, so really no change. And then again, 80 again at the alum for the force jar, but a little higher on the 8170. And really no improvements at all. So what I can say is that adding this other polymer, which is utility was actually using, I can say, this polymer you're using is not impacting the results. It's actually, if anything, it might have made it worse. So sometimes when you add a different, you add something with your coagulant, it could sometimes have a negative impact on the results. So, but this is just a way to kind of see, to demonstrate, what 80 is. Basically we got pretty consistent results as far as the UVA, and then evaluating whether this polymer, what kind of impact this polymer has. And then another set I did was a totally different coagulant. We call it 9800, and I wanted to just kind of see what kind of performance we get out of this one. And what I did is, you may wonder, how did I come up with this dose? And this dose is basically about equivalent, if you're looking at the amount of aluminum I'm adding for the alum, say for about 80, this is about the same amount of alum or aluminum I'm adding with this product right here. So, between 55 and 60. So I did 55, got great filterability, 0.04, better, pretty good settleability. but the UVA is high. It's 0.039, where I'm getting 0.032 on with the alum product. So, and then I did at 60, and great filterability, 0.04, pretty good settleability. Slightly improved on the UVA, 0.038, but still, this 0.38 is still higher than 0.032 with the alum. And then I looked at the same dose of 9800 with another blended polymer that has some polyamine and some ACH in it. I looked at a dose of 3 with a combination of 55. Same, filterability 0.04, slightly improvement 0.037, and then I did the 60 9800 with the 3 parts of the 9890. And good filterability. Still, the UVA is 0.036. Now, I only did 1 set of jars of this product. If I wanted to evaluate this more, I would look at maybe a higher dose and see, what are my limits. Sometimes with these polymers, you go too high, all of a sudden everything, your filterability, you get a weak flock. Or if you're too low of a dose, you get a weak flock. So a lot of times with these polymers, you have a smaller window of performance with the dose of the coagulant. And then let's see here. And then today we just did again. We went for the demonstration of this video. We just did the 50, 60, 70, 80 with the coagulants, and just to kind of show. Mainly, I knew that the turbidity would be pretty good, but I wanted to kind of demonstrate the improvements on the UVA value. So we went from 0.045 to 0.034 at 80. So again, we just don't stop at the best. What coagulant gives you the best filterability, especially if you got organics in the water. You want to also look at the UVA, and you need to figure out, what is the dose that gives you the best, optimize both filterability and UVA. In surface water treatment, there are at least 3 goals that the operator should have. 1 is filterability, 2 is organic reduction, and if you have settleability, if you have settling, then settleability. Filterability, there's a turbidity performance standard that all surface water facilities have to meet. And that can range from 0.1 NTUs to 0.3 NTUs, depending on what type of technology. However, if you have a well-run plant, the plant's operating, if you have the right coagulant and dose, you should be making well under 0.1 NTUs all the time. And the second part is that any plants that have organics, you want to reduce as much organics as possible to minimize disinfection byproducts. When chlorine reacts with any kind of dissolved organics that's coming out of the filters, you're going to get disinfection byproducts. And third, if you have settling, you want to reduce as much solids flowing to the filter as possible. To determine what coagulant dose will help produce the best performance output for filterability and organic reduction, you want to do jar testing. Jar testing is a great tool for determining what coagulant dose and any other preoxidant and coagulant A's that will help the utility make the best filtrate water and also organic reduction. So in jar testing, we have 3 things that we're looking at. We're looking at filterability. We have a membrane that we use that will mimic a media filter. And then we're looking at UVA as an analysis as a surrogate for DOC. And then also if you have settleability, we're looking at each jar, gives you the relative settleability for each jar. We're not just looking at settleability. Does it give you any information on filterability or organic reduction? And to be proficient with jar testing, an operator needs to spend several hours just doing jar testing, doing daily jar testing. I recommend they do 100 hours of, put in 100 hours of just jar testing. They could look at different coagulants. They could look at, mainly, jar test what coagulant they're using, but they can also experiment with different coagulants in dosages, and look at other pre-oxidants as well. And once they have that down, once they're proficient in doing jar testing, then you need to do jar testing at least once a week, because when you have a water quality issue, like you have a rain event or algal bloom event, and you need to, and things have changed, and you need to make a quick chemical change, you want to be prepared. You want to be able to go in and do a jar test. You don't want to go in and not know how to do a jar test. And so by doing it once a week, you're practicing, you're keeping it fresh in your memory. And so when it's time to really make a change, the operator will be comfortable in doing a jar test and determining what coagulant dose that they need to adjust to optimize their treatment facility based on the water characteristics that are coming in. There's a lot you can do with jar testing, not just adding a coagulant, but we can look at other different chemicals and pre-oxidants and also acids as well to optimize for example, organic reduction. So you could do jar testing where we call enhanced coagulation, where we can drop the pH by adding acid, and to evaluate the impact that acid has on the coagulation process and organic reduction. We can jar test, jars with and without acid, and evaluate the performance of organic reduction, and also at the same time looking at filterability and settleability for plants that do have settling. Also, we can look at activated carbon. And so in jar testing, we don't have an activated carbon filter, but you can look at powder activated carbon. And we can look at just adding the powder activated carbon with the coagulant up front and see what kind of performance the activated carbon would have if you're thinking about putting in activated carbon on the back end of your primary filter, or even using powder activated carbon as part of the coagulation process. One of the things you want to consider when using powder activated carbon is look at the injection point, whether you're going to add it before the coagulant or after the coagulant, because it can make an impact on how well, it does make an impact on the settleability. So if you add the coagulant, we have some studies where we add the powder activated carbon after the coagulant, but it also causes a spike in settled water turbidity. But when you add it before the coagulant, it didn't impact the settleability. So that's something you want to consider if you're looking at full-scale operations, the point of application. So you have your powder activated carbon, you have your acids. Then you can try out lowering the pH, use the same coagulant dose, but looking at different coagulant or different acid dosage and pHs and see which one provides the best performance. And then again, we talked about pre-oxidation with the potassium permanganate, where if you're considering potassium permanganate, as you may know, potassium permanganate takes a while for it to work, for it to oxidize in the water. And so if you were thinking about adding that chemical, look at what the hydraulic residence time is from the point of injection to the point of your coagulation injection point. And if that's, say, for example, that's 30 minutes, then you would want to jar test just by itself to the potassium permanganate for 30 minutes at different dosages. And then after that, add your coagulant and see what kind of results you get out of that. So there's many ways of jar testing, looking at various chemicals, coagulants, combination of coagulants, and oxidants and things like that. For systems that have ozonation, you want to, if you want to see what the impact of the pre-ozonation has, take water before and after ozone and jar test that and see what kind of impact the ozone is having on the organic reduction, the filterability, and how much coagulant. And sometimes many times the ozone will allow you to dose at a lower coagulant dose for the same results as if you didn't have ozone and dosing at a higher dose with a coagulant. So there's many things you can look at and evaluate your plant, whether something is working or not working. Back to the filterability analysis. The size of filter that we want to use is the 1.2 micron absolute isopore membrane. This filter is the best filter for modeling a media filter in full-scale operations. If you were trying, the purpose of this is to figure out whether we have a strong or weak flock. Any flock that goes on into the filter, we want to know whether it's going to be filterable or not. And this is the analysis that we do. If it's a weak flock, you will see a breakthrough through this filter and shows up as increase in turbidity. If it's a strong flock, it will be held on the filter. Now, if you use any other type of filter, like a tighter membrane, that's tighter than 1.2, you're going to end up removing both strong and weak flock, and you're not going to be able to distinguish between a strong and a weak flock between each jar. And if you go with a larger membrane pore size, that's greater than 1.2, it's going to pass both strong and weak flocks. So you're not going to be able to distinguish again between a strong and a weak flock. So this is the filter you want to use. You don't want to use a nominal size filter. You want to use an absolute 1.2 isopore membrane. Now for the source water, we want to use a 0.4 micron filter. They look the same, but it'll say 0.4 micron isopore membrane. And this is just to remove the suspended solid so we can measure the UVA. So we want to, and the reason for that is that we want to compare dissolved UVA with filter UVA. So we know what we're starting with and what we're going to be ending up with in the filterability analysis. And so that helps us determine what kind of reduction we have in UVA, or you can think of it as the DLC reduction. All right, before we start our jar testing, we need to first make up our stock solution, the chemicals that we're going to be adding to each of our jars. And the primary chemical is going to be our coagulant, and then anything else could be a coagulant aid or preoxidants such as potassium or sodium permanganate and things like that. So the solution strength that we're going to make in our stock solution is going to range from usually from 0.1 to 2 to 3% strength. And at that strength, it's a weak solution, and so we can assume that anything that's, say, 3 or 4% less, that 3 or 4% strength solution or less, is the same weight of water. So let's go over the weight of water. So if we have 1 milliliter of water, say H2O, that has a weight of 1 gram or 1,000 milligrams, right? So if I have a 1% solution, for example, let's take 1%. So if I have 1% stock solution and I have 1 milliliter of that solution, so the amount of chemical by weight in that's 1 milliliter is going to be 0.01 times the weight of the water. We're going to assume that stock solution has the weight of water. So 1 mil has the weight of 1,000 grams or milligrams. And so that's going to equal to 10 milligrams of our chemical. So when I'm doing jar testing, I'm using 1 liter jars. And so if I'm going to say I want to add, let's say I want to do, I'm just going to make up these numbers. Let's say I want to add 20 milligrams of chemical to this liter, which would be 20 milligrams per liter, because these are liter jars. And then I'm going to add 30 here, let's say 40 on this jar, and then 50 on this jar right here. And so I want to make up a stock solution, so it makes it easy for me to, when I'm pipetting, is how many mils I need to add to each jar. So if I have a 1% solution, and so if I add 1 milliliter into 1 liter jar, that's of a 1% solution. That's the same thing as adding 10 milligrams. Are these racers? Same thing as add 10 milligrams of my chemical into 1 liter. So for every 1 milliliter I add, I'm adding 10 milligrams. And so when I pipette this, I have a pipette that ranges, for example, this ranges from 0.5 to 5 milliliters. And so, so if I want to add 20 milligrams, I just simply add 2 milliliters, because 2 milliliters has 20, it's equivalent to 20 milligrams of chemicals. And the same thing for 30 milligrams, I'm going to add 3 milliliters, and same thing for 40, it's going to be 40 milliliters, and then 5 milliliters for that. So this is a 1% stock solution. So I'm using 1 liter jars, using a 1% stock solution, so everything, it makes it much easier when I'm dosing my chemicals during the jar testing. Now, let's say I want to add a coagulant aid. And the coagulant aid I want to add is, we're going to dose, say, 10% of what my primary coagulant dose is. And so say my coagulant aid is going to be 2 milligrams here, then this is going to be 3 milligrams, and this is going to be 4 milligrams, and this is going to be 0.5. So if I had a 1% stock solution, so let's say I made a 1% stock solution, that means I have to add 0.02 milliliters to get a 2 milligram dose, and a 0.03 milliliters to get a 0.3 milligram dose. And I do have a smaller pipette that ranges from 0.1 to 1. It has a smaller range, but it's still not low. It's still not in the range for me to add this kind of dose if I'm using a 1% solution. So what I would do is make a 0.1% solution. And so if I had a 1% stock solution, that means that, so of 1 milliliter, so remember 1 milliliter weight of water is 1,000 milligrams, so 0.001 times 1,000 milligrams is simply just equal to 1 milligram. So for 1% stock solution, if I add 1 milliliter into 1 liter of water, or source water, I'm basically adding 1 milligram per liter. So by using a 1% or 0.1% stock solution, I'm adding now just 0.2 mils per liter. So it's a 1-to-1 ratio on as far as the volume and dose. And this is going to be 0.3 milliliters, 0.4 milliliters for a 0.4 dose, and then a 0.5 milliliter dose. So right now, so this is the 1% solution, and basically you just, if this is 20, we're going to add 2. You know, it's a multiple of 3 times 10 to get the to calculate the mils to dose. Now, if I was going to say I was working in a range that's higher than 50, say I want to do 60, 70, 80, 90, or something like that. I can still use a 1% stock solution, but that means I would have to pipette twice. So because this pipette goes up to 5, and let's say I want to do 60, I would have to change this to say 3 mils and dose twice to get 6 milliliters. Or the other option, if I don't want to pipette twice, if I know I'm going to be in a higher dose all the time, I can make a 2% solution, meaning that if I have a 2% solution, that means that each mil I would add would be a 20 milligram dose. So, so that means that if I was doing 60, I would just add 3, and that's times 2. That gives me a 60 milligram per liter dose. So you just simply double the percent strength. All right, so the next step is to, how do we make up our stock solution? And I'm going to erase this. Stock solution. So there's many different types of coagulants out there. we have our common ones are alum, aluminum sulfate that most people are familiar with. Then we have our ferric chloride, ferric sulfate coagulants out there. They all have a certain percent strength. And when we report those coagulants, we always report them as dry chemicals, like aluminum sulfate. We report it as dry. Same thing with ferric chloride and ferric sulfate. But then we have all the other coagulants that are out there, the ACHs, the polymers, the inorganic, organic polymers. And then we have our blends as well. And there's so many different concentrations out there. And many of the blends, they have a trade secret, so they don't really tell you what's in it. They'll say part of it is this, but then the other part is a trade secret. So it gets down, so it makes it difficult to try to figure out which ingredients is what in the products as far as percent-wise. And so it's best you just assume 100% when you're dealing with polymers and stuff like that as the strength. We just assume 100% strength for products, polymers and inorganic and organic polymers. With alum and ferric chloride, we'll just assume we want to report those as dry chemicals. So we want to know what the percent strengths are. So let's take an example of a product, say aluminum sulfate, that most people are familiar with. So aluminum sulfate will have a certain strength of say 48%, and that's kind of a common percent strength. It also has a specific gravity, say 1.32. And the specific gravity, if you don't know what that is, it's just the relative weight compared to water. So if I have a specific gravity 1.32, that means it's 1.32 times the weight of water of the same volume. That's all it means. So, and then I want to figure out how much of this this product in milliliters, I want to add to make a certain stock solution. So, and we're going to use, for example, my volumetric flask right here. We're going to figure out, say, how much of this chemical right here we're going to add to make a, say, for example, say a 1% solution. And because it's such a weak solution, we're going to assume that the specific gravity of this stock solution is going to be 1. And the volume that we're going to be using on this particular example is going to be 200 mils. So this is basically our equation for stock solution preparation. And what you want to do is look at the units, make sure all the units are the same. So we have percent here, percent strength here, percent strength here. We have specific gravity, which is unitless, specific gravity here. And then we have milliliters, how much mils we're going to add of this to make a 200 mil solution. So the units are all the same. And so the next step is simply to solve for x. And that's just going to be 200 divided by 48.5 divided by 1.32. It's a simple algebra. And this is going to be about 3.12 milliliters. And so that means that I need to pipette out about 3.12 mils of my alum into this flask. And what I normally do is fill about halfway with DI or distilled water, and add my 3.12 mils of coagulant. I'll mix it up a little bit and add it up to the line for the 200 mil section. So this is alum. Now, if I wanted to do like the other products, like the polymers and things like that, we're going to assume that it's just going to be 100%. So if I wanted this, which makes it a little bit more easier. So let's say it's 100%. So I have a product that's 100, we assume 100%. And say the specific gravity again is 1.32. And we're going to figure out how many mils to add to make a 1% solution. And the specific gravity, again, it's 1, because it's a weak solution, and 200 mils. So the amount of product we need to add to make a 1% solution is going to be x equal to 200, just divided by 100, and its specific gravity of 1.32, and that's just going to be around 1.5 milliliters. So this is a 1% solution. Now for this one, if I was going to do a 0.1% solution, and we assume 100% strength, that means I would have to add, instead of being 1.5, I have to find a pipette that can pipette out a 0.15. And you may not have one that goes down to that range. And so what you can do is that you just simply make a 1% solution, and then take that solution and make another solution from a 1% to a 0.1% solution. And that might be simply like this. So now you have a 1% solution with a specific gravity of 1, and you're going to figure out how many mils you want to pipette to make a 0.1% solution with a specific gravity 1. And say my volume on this time, instead I don't need 200, maybe I want to make a 100 mil solution because we're dosing very low dosing, the amount of mils we're adding is very low, so we can get by with a 100 mil flask. And this is just going to be simply 100 times 0.1, it's just going to be 10 divided by 1, and so our amount that we have to transfer from here to make a 100 mil solution is just going to be 10 milliliters. So it's basically a 10-to-1 ratio. And this would be a 0.1% solution. So you're basically making two stock solutions. You make a 1% first, and then you further dilute that down to make a 0.1% solution. So for this example, we have a primary coagulant of 20, 30, 40, 50, and then we're going to possibly add a coagulant aid, which is 0.2, 0.3, 0.4, 0.5 milligrams per liter. So anytime you're adding two coagulants, a primary coagulant and a coagulant aid or filter aid, you pipette first your primary coagulant into each jar, and then you come back and pipette the coagulant aid of the 0.2, 0.3, 0.4, 0.5 doses, and then you start your flask mixing. So you do it in that order. You don't go primary coagulant and then coagulant aid and then go back and forth like that. You do the primary coagulant first and then your coagulant aid. Previously, we talked about making stock solution out of using liquid products. Now, what happens if you have a dry product? How do you make a stock solution out of that? Some of the dry products could be some of the organic polymers, could be maybe potassium or sodium permanganate that comes in a dry form. It could be powder activated carbon, anything that comes in a dry form. And you need to make a stock solution out of that. So let's do an example of one, which is we have basically we have some weight in gram that we're going to add to a certain volume of water for a stock solution. And in this example, let's assume that it's going to be, say, 500 milliliters of water. So this is some weight we're going to add into a certain volume to make a certain percent strength. And let's say that percent strength is 1%, for example. So if you remember, water, 1 mil of water, has a weight of, say, 1 gram, right? Or 1,000 milligrams. So we can say, so 500 mils of water is basically the weight of 500 grams. So if you want to figure out how many grams you have to add into this volume of water to get 1%, we just solve for x. And so x is equal to 1%, so convert that to decimal point of 1. And 500 mils is the same thing as 500 grams, so it's 500 grams. And so x is simply 5 grams. And so you have a little scale. You can buy little pocket scales, or you don't have to buy anything that's expensive. But just buy a little pocket scale, and you can measure out 5 grams. You'll put it into a beaker, and normally the beaker will be sitting on a stir plate, magnetic stir plate. You have a little magnet inside this beaker to stir, and you have your water, weigh out your chemicals, add it to the beaker water, let it mix up, and then you have your 1% stock solution. For any certified treatment operator, they have to do daily dose calculations. And so if you have so in this video we're going to talk about how to do a dose calculation. And so you have a pipeline of water flowing through a pipeline, and you have chemicals that are being dosed into this pipeline. So when we're doing dose calculations, we need to know, based on this flow of water and how much chemicals are coming in, what is their chemical dose. And chemical dose are normally reported as milligrams per liter. So the standard setup, the setup that will always work for any type of calculation of chemical dose, is just milligrams per liter is equal to the amount of chemical that's being added, which is going to be some, we're just going to call it chemical feed rate, divided by wherever this flow is, plant flow. So this is the standard setup. Anytime you want to calculate dose, you start out how many milligrams per liter is equal to the chemical feed rate divided by the plant flow. So chemical feed rate over plant flow. All right, so the chemicals, we need to know something about the chemical that we're feeding. We need to know what its percent strength is of what's being added, and we need to know what the specific gravity is, and we need to know what the feed rate is. So let's do an example. Let's say that the feed rate on this one is, say, 200 mils per minute that's being added. Let's say the specific gravity on this one is a 1.32, and say the strength on this one is 48.5%. So the chemical feed rate is simply 200 mils per minute divided by the plant flow, and we're going to say the plant flow on this one is, say, 1,000 gallons per minute, which is the same thing as GPM. So the feed rate is 200 mils per minute. The flow rate is, say, 1,000 gallons per minute. And so what we have is 200 mils per minute, gallons per minute. And what we want to do is convert the numerator, have units of milligrams, and the denominator, which is in liters. So the first thing I do is look at the time values. This is the minutes, and this is the minutes. We don't have minutes in here, but the minutes here will divide out because they're the same units, and so they'll just divide out to be 1. So now we're just left with gallons, and we have liters here. And so now we want to convert gallons into liters. So we need to know, every operation know that there's 3.785 liters in 1 gallon And so now if you look at the units, the gallons divide out, and we're just left with liters. So the bottom, it's done. We have just liters. Now the next step is to convert 200 mils into milligrams. We know water has a weight. We know that water, there's 1,000 milligrams in 1 milliliter, right? And that's water. But this is a chemical solution. It has a different weight of water. And so because of that, we need to multiply this by the specific gravity, 1.32. So really, there's not 1,000 milligrams per milliliter. There's 1,320 milligrams per liter, if you just multiply this by that. Also, this is not, it's not 100% solution strength, it's 48.5% strength. So we need to multiply by that and put that in a decimal point to get the actual chemical concentration. So now look at your units. The units divide out, we have mils divide out, and the only thing we're left with is we're left with milligrams on top and liters in the denominator. So we have milligrams per liter, milligrams per liter. And so when we do the calculations, we multiply everything on the top, divide everything by the bottom. 1,000 divides out here, so we don't need to go through that calculation. So 200 times 1.32 times 0.48, 0.85, gives us 128.04 on top, and on the bottom is divided by just 3.785. And that number, divide that by 3.785, and we get a dose of 33.8 milligrams per liter. So that is our dose. And so this 200 mils per minute, that's normally a physical drawdown. The operator goes out and it does a physical drawdown of the chemical feed pump to see what's actually being fed into the water. Different example, let's say the chemical that we're adding has 100% strength. And the specific gravity is, say, 1.32. And it's being fed at, say, let's say 3.5 gallons per hour. Do this again here. And we want to know what and the flow is 1,000, say the flow is still 1,000 gallons a minute, and we want to know what the chemical feed rate is, or the chemical dose. So again, the dose setup is basically the chemical feed rate divided by the flow. So the chemical feed rate on this one is 3.5 gallons per hour divided by its flow, gallons per minute. And that's your setup. Every time it's always the feed rate divided by the flow. Now on this one, on the previous one, the units of time was minutes and minutes, but this is in hours and minutes. So first we need to convert one of these units so they're the same so they can divide out. So we got to convert minutes to hours here or hours to minutes here. I'm going to go ahead and convert hours to minutes here. So I'm going to multiply, I'm going to multiply by, I'm going to say there's 1 hour into 60 minutes. And what I'm doing is called dimensional analysis. So it's basically converting one set of units to another set of units. All right, so now the hours will divide out, and now we're just left with minutes and minutes, and the minutes will divide out. And so the next step is gallons to liters. And again, we just say there's 3.785 liters in 1 gallon. And so now the gallons divide out. The next step is that we have gallons, and we're going to need to convert that to milligrams. All right, so let's think about how many, I like to go to liters. So how many liters are in a gallon? Well, we know there's 3.785 liters in 1 gallon, all right? So now we get rid of the gallon unit, and we're left with liters. And then we can say, well, there's 1,000 milliliters in 1 liter. So now we get rid of the liter unit right here. And now we can say there's, say, 1,000 milligrams in 1 milliliter. And that's the weight of water. Because this is a chemical that has a weight that's heavier than water, we need to multiply by its specific gravity, which is 1.32. And then we need to multiply by strength. So the strength's at 100%, so we're just going to convert that to decimal point, and that's just going to be times 1. So what you want to do before you do the calculation, make sure all the units are divided out, so you just end up with milligrams per liter. And so what I have left, so the milliliters here divide out, and so on top, what I have left is just milligrams, and on the bottom, I just have liters, and that's what we want, milligrams per liter. And then the next step is to just do the calculations. So we have milligrams per liter, and let's do the calculations real quick. So we got 3.5 times 3.785 divided by 60. So we can say this divides out, so we don't have to use that number, times 1,000 times the specific gravity, 1.32. And this is on top equals 291.445. And on the bottom, we just have the liters, 3.785. Divide that by 3.785, and our dose is 77 milligrams per liter. So just by the previous example, it was 200 mils per minute, and it made everything much easier, but now we had something that was in gallons per hour, and so we had to do some unit conversion. We had to convert the hours to minutes, and then we had to convert the gallons to the metric system, like liters. And then from there on, we were able to convert the liters and eventually have milligrams. And so this is called dimensional analysis. A lot of operators, sometimes they're used to just plugging into an equation, not really knowing what they're doing. This is the best way to do it. And to really get good at this, you really have to practice just like anything else. You just have to, every day, just go through a hand calculation and doing a dose calculation. I know there's computers, there's software out there that will do the calculations for you, but you do want to verify what the software is putting out with a hand calculation. And to do that, you need to practice every day doing this. Let's say you're working at a treatment plant and your boss tells you that we need to increase the chemical feed rate or the chemical dose from X to Y. And you need to determine what the chemical feed rate needs to be. And so, if you remember, your dose, milligrams per liter, is just simply your feed rate divided by the plant flow. All right. So your boss comes and says, I want to change my dose, say from whatever it was to, say, 60 milligrams per liter. And your job is to determine what the feed rate needs to be over a certain flow. So for this example, let's say the flow is 100 gallons a minute. And the chemicals you're using, let's say you're dosing as the solution strength, let's say is 100%, using some kind of polymer. And so we're just going to assume 100% as product. The specific gravity is equal to 1.32. And your feed rate, you calculate your feed rates in mils per minute. So we have our feed rate. It's going to be some kind of X mils per minute over our flow, which is going to be 1,000 gallons per minute. So the way I would do this is solve it as if you're solving for dose. Pretend that you didn't know what this is. You're just going to solve for milligrams per liter. And And then at the end, you're going to solve for x. So again, like we did before, well, let's divide out the minutes. We have a time value, so let's divide out the time value as minutes. And then the gallons, we want liters, so we want to go 3.785 liters in 1 gallon. So the gallons divide out, and we're left with liters. And the next step is to convert milliliters to milligrams. And so we know there's 1,000 milligrams in 1 milliliter for water. Since it's not water, it's a solution that's heavier than water. We need to multiply by 1.32. And then the strength on this one, we assume 100%, so we just multiply this by 1. Now, look at the units. The mils divide out milligrams, then we're left with milligrams. So what you want, so to solve this, so we've got milligrams per liter, milligrams per liter. So next, we just, to solve how many mils per minute, we just solve for x. And so x is just going to be 60 times everything on the bottom divided by everything on top right here. So we know, before we do that, we know the 1,000 divides out. And so x is just going to be right here, 60 times 3.785 divided by 1.32. And we'll do the calculations. And so we'll go 60 times 3.785 divided by 1.32. And our x is 172, which means we plug back in x right here, and that is 172 mils per minute that you need to set your feed pump at to get a dose of 60. So that's the simplest way to do to determine what your feed rate needs to be. All right, in this next video, we're going to talk about how to calculate the new percent strength and specific gravity of a solution that you mix up and that was diluted down. So for this example, let's say you bought some alum. We just use alum for this example. And it has its specification is that it's 48.5% strength, has a specific gravity, say 1.32. And you buy some alum and you dilute it down. So let's say, for example, let's say you have you take 1 gallon of alum, and you're going to add it. You're going to add, say, 9 gallons of H2O or water, and you're going to mix it up. And when you do that, you're going to have a new specific gravity and percent strength, and you need to determine what that is so you can do your dose calculations. So percent strength, it's basically just the weight of your chemical divided by the total weight of the solution. So weight of the chemical solution divided by the total weight. All right, so say we have a gallon of alum, and that gallon is a gallon of water has a weight of, well, we have 1 gallon, and it has a specific gravity of 1.32. All right, we could do it this way. There's a couple ways of doing it. This is kind of a little bit simpler way. So you have a gallon of water, and it has a weight of 1.32. So it means that it's 1.32 times the weight of water. And that's their weight. And then, but we're looking at, the other thing is, we're looking at alum at 48.5%. So we're not reporting alum as product, because product would be like 51.5% water and 48.5% alum. So we want to report it as dry alum. So we want to multiply this by the percent strength, which is decimal point 485. All right. So that tells us how much actual weight of the dry alum is. And we're going to divide that by the total weight. So we have 1 gallon of alum. It has a specific gravity 1.32 plus water, the weight of water, which is 9, just 9 gallons. So all the units, as long as the units are the same, we can use volume versus like weight in pounds or grams or kilograms like that. So the units all divide out, and we multiply this, and this is actually times 100%. So we multiply this by 100%, and then we'll do a calculation. So we'll just go 1.32 times 0.4 times 0.45. .485, that is, divided by, so this is 1 point, so that gives me 0.6402 divided by, so this is 1.32 times 1 plus 9, and so that's again 0.6402, and this is 10.32, and then again this is times 100%. And we'll divide that by 10.32 times 100, and our new solution strength is 6.2% alum. All right, to continue, we calculated the new percent strength of alum by when we diluted 1 gallon of alum. That has a strength of 48.5%, specific gravity 1.329 gallons of water. The next step is that we need to calculate now the specific gravity. So I'll do the specific gravity down here. So the specific gravity is just the total weight of the solution divided by the weight of water of the same solution volume. So, so let's look at the total weight of the solution. So we have on here, if you remember, we had 1 gallon of alum and 9 gallons of water. So let's look at the total weight of that. And so we can just say, look, we have 1 gallon of water, so it's 1 gallon. It has a specific gravity of 1.32 plus 9 gallons of water. And I'm just going to put gallons here, and gallons of H2O. And this is a little simple way. You don't have to actually put in the weight as such as pounds and grams or whatever. We could just use volume and specific gravity. So we have 1 gallon of alum. This is alum. This is just water. And so this is your total weight divided by the weight of water of the same volume. So the total, the weight of water would just be 1 gallon of alum, which is going to be just water, assuming it's water, and 9 gallons of the water that we're adding to the alum. So just 1.32 divided by, it's 1.32 plus 9 divided by 10. So this is going to be 10. And so, so we have 9 plus 1.32 is just 10.32 divided by 10. And you calculate the specific gravity for that. And that just becomes 1.032, which is getting pretty close to the weight of water. So this is a 6% solution strength of alum, so that makes sense. So it's pretty close to 1. And that's it. So we, you know, you could take If you want to convert everything to weight, you're going to get the same numbers, but this is just a quicker, easier way to do it by using specific gravity of the original alum that you're mixing up with the water. And so water has a specific gravity of 1, right? So it's just 1 times 1.32 for the alum plus 9 plus 1, and you add that up, and then divide it by the weight of water of the same volume, which is just 1 plus 9 times its specific gravity, just be 1 because it's water. And you get 10.32 divided by 10, and the new specific gravity 1.032. And so when you do your dose calculations, you're going to be using this specific gravity and this percent strength when you calculate your dose, when you do your dose calculations. So after I'm done with jar testing, I transfer all my results from my notebook into a PowerPoint presentation, and along with all the pictures that I've taken. So this is just a setup from when I did the jar test from yesterday, where we have our 4-jar tester. We have our syringes for pulling the coagulant water for filterability analysis. We have our filter holders. Each one have the 1.2 micron filters for the filterability analysis, and also doing a filtrate UVA analysis. We have our pipette for dosing our coagulant, and also making up our stock solution as well. Here's there's our notepad for recording our results, our turbidity. We have our instruments. We have a turbidity instrument. We have a UVA, UVT instrument. And we have our cuvettes for the doing a settleability analysis. And then we have one clean cuvette for the filterability analysis that we use. And our phone for use as a timer to tell us how long to flock for and how long to settle for and things like that. So everything is kind of here on everything you need for jar testing is here. And then the source we end up using is called North Bay Aqueduct. This is just the picture of what the source looks like. This is the plant that we worked with. It's called American Canyon Water Treatment Facility. They have 2 plants, and one is a conventional treatment plant, one's the membrane filtration plant. And so basically we brought water back to determine what coagulant and dose gives them the best, say, filterability and organic reduction, at least for the conventional plant. So the first thing I do is do the source water analysis. So we do a pH analysis, do an alkalinity analysis, turbidity, see what the turbidity of the source water is. And then we do the UVA and UVT. Now, to compare, like, as far as the UVA is a surrogate for DLC, dissolved organic carbon in the water. And to compare the dissolved, like, DLC from source water to treated, we actually want to look at the dissolved form. And so to get the dissolved form of UVA, we run the source water through a membrane filter, and we use a 0.4 micron absolute isopore membrane, and we'll measure what the new UVA would be, which is the dissolved. And that's why I want to compare that value with the filtrate UVA value. So we want to compare the dissolved source water UVA with the filtrate UVA. And then the plant water, settle water turbidity, the day I took the water was 1 NTUs. The plant filtrate water was 0.07 NTUs. The UVA was 0.034. And then also did the post-plant filtrate post-chlorine water, and to see what the reduction in UVA would get after chlorination. And it went from 0.34 to 0.26. This means that there's organics in the water, and the chlorine reacted with some of the organics, converting some of the organics to THMs. Therefore, you have a lower UVA. So this lower UVA doesn't mean better water. It just means that some of the organics was converted to THMs. So the main thing we're looking at, as far as performance-wise, as far as organics, is the post-plant filtrate water before any kind of chlorination. So some of the coagulants that I use for the jar testing, we use a 7% acid alum, and these are the specifications of the acid alum. It's 36% alum, and 7% sulfuric acid was the specific gravity 1.3. And then we looked at some polymer as well in one of the jar testings, used as a filter aid. And then we also looked at a couple other coagulants. They're much different than alum. These are the aluminum chlorohydrate. And we also looked at a blended polymer, which is a aluminum chlorohydrate along with the polyamine. So this is called what we call a blended polymer. The instrument we use is a UV-UVA instrument for measuring primarily we want to measure the UV absorption of the water. And you can think of UVA as the amount of, if you have a UV light of 254 nanometers and you shine that through a media of water, if you have, if there's no organics or metals in the water, the UVA value would be 0 absorption. So think of bottled water. If I were measuring something, organic free water or bottled water, the UVA value would be 0. But if I have any kind of organics in the water, some of that UV-254 light would be absorbed by the organics, and then we would have a value. The other parameter that we measure is called percent UVT, UV transmittance. Again, you shine a UV light at 254 nanometers. If we have 0 organics in the water and no metals, all that 100% of that light will come through, and you will have a value of 100%. If I would measure bottled water, or organic free water, it would be about 100%. So anything that gets absorbed, it would be less than 100%. So some of that UVA, if some of that UVA was absorbed, then the percent UVT would be less than 100%. Most surface water plants, they're in the 90+%, and the higher the better. But UVA is a linear measurement in regards to as a surrogate for organics, dissolved organics in the water. So that's the one that we actually use to measure, to get a sense of how much percent reduction we're getting between source UVA versus filtrate UVA. This is a laboratory charge analyzer that before I even do jar testing, this is a laboratory charge analyzer I use to determine what coagulant dose is needed to neutralize the charge. So basically we have a 1 liter jar of source water, we have a chemical feed pump that will dose automatically the coagulant into this jar, and we start out measuring a negative charge, and so here it says like a minus 182, and once this charge becomes 0, it will display the chemical dose. And for this example, for this water, the dose was 37 milligrams per liter of alum. That just means this is the amount of dose needed to neutralize the charge. Doesn't mean we're at the right dose for optimization when it comes to organic reduction or anything like that. But it's the minimum dose needed to neutralize the charge. So this is kind of where I start my jar testing. And then we did a product called 9800, which is an aluminum chlorohydrate, and it also provides a starting point as well. So when I'm reporting, anytime I'm reporting coagulant dose, unless stated otherwise, I'm reporting the dose as product, the chemical product, the name of the product, unless we're working with aluminum sulfate like alum or ferric chloride. So for this particular water, they are using alum, and so we're going to reporting as hydrated aluminum sulfate, not as product. So the first thing as far as the results, I put everything in a table form, and so we have the first 8 jars, first 2 sets of jars, sets of 4. So we started out with a dose of 35, and we worked our way down, and in the second set, the first set we went from 35 to 50, and then the second set from 55 to 70. And this is the dose for the alum, and then the equivalent, the dose, calculated dose for the sulfuric acid. And then we have our filtrate turbidity. This is taking the flocculated water and running it through a 1.2 micron filter. And we want to see, and an important thing is that you want to know whether the flock that's being carried over into the filter is filterable. And so at the lower dose, it's not very, the filterability is not very good until we get up to 50. And 50, now we're getting 0.06, 55, 0.07, 0.07, so we're below 0.1. Now the second thing we're looking at is the UVA values. So here we start at 0.055, and we want to get this value down as low as possible, or lowest, or lowest as, whatever it's reasonable to get this down to. And as I mentioned before, is that anything that's less than 0.03, there's less likely of a system being over the, being out of compliance with disinfectant byproducts. But the lower the value you can get, the less disinfectant byproducts will form out in the system. So we know we're going to get a lot of disinfectant byproducts with this value versus maybe a value of 0.035. This is the percent reduction. You can think of this as like DLC reduction from source water to filtrate water. And again, the UVA is a surrogate, used for DLC. DLC is a very expensive instrument to have, and most utilities don't have. They don't have that instrument, and they can't readily do DLC analysis. And it does take time. The UVA analysis is very quick, and the instrument that's used is very affordable. And then we have a settleability analysis. So the settleability is basically a relative, a value that's relative to each jar. So the lower the better. We can look at coagulants that will provide the same kind of filterability performance and maybe UVA performance, but also has a much better settleability. So these are things with jar testing you can evaluate, not just your coagulant, but you can also look at other products and see maybe there's another product that will provide a better performance as far as maybe if you're concerned with settleability. And not all plants have settling. About half the plants, at least that I work with, they don't have settling. So the main parameters you're looking at is the filterability and UVA. So settleability is not something that about 50% of the plants that are out there have. They have different technology. So we continue on with the jar testing. So we did a higher dose, 75, 80, 85, 90, on the third set of jars. And so one thing you might look at is the filterability. We did get a little bump on the 80 here. It's 0.04, then 0.08 at 80, and then 0.04 again. But what I'm looking at also is the UVA. So the UVA dropped to 0.34, and then it went to 0.032, and then it didn't improve any more from 80 to 90. So this is key information for the operator to know that, well, if you went to 90, you're not going to improve as far as, you're not going to make any improvements in regards to organic reduction. So there's no use of going to 90, but 80 looked like at 80 is where the max you can dose that gives you the best, UVA. You're just not going to, there's organics in the water that you're just not going to remove, and 80 is about its limit right there. And so what I did is I took 80, even though this filtrate turbidity was 0.08, I did 80 again, and the next sample was 0.04. And then I did 80, I want to compare with this other product, which is called 8170. It's a polyacrylamide, and its utilities happen to be using it. So I wanted to look at what kind of impact if I was adding this polymer. So my first jar was 80 without it, and then the second jar was 80, 80, 80, but with the different dose of the polymer, and just wanted to see what the impact was. And from the analysis, there really was no difference in with it or without it. In fact, it was slightly, if you look at the UVA, it was slightly better with it without actually using this polymer. So there's a possibility that the utilities using this polymer and really it's not doing much. And you have to be careful with polymers, because especially with the polyacrylamide, that it can actually glue your media together. It's if you overdose, and then you have another problem where you may have to replace your media because now it's all, the media has all binded up. So so unless unless you're having a flock issue as far as a weak flock, it's sometimes it's best not to use a polymer if it's not needed. And then I did another jar test, just using a totally different coagulant that the system doesn't use. I used something called 9800, which is the aluminum chlorohydrate. And I just did one set of jars, and I would do more jar testing to further investigate. But what I have shown now is just, I did a 55 and a 60. And then I did a 55-60 with a what we call a 9890, which is a blended polymer of ACH and the polyamine. And I just want to kind of see what kind of performance I would get out of it. The dose, you may ask, how did I come up with 55-60? This 55-60, it's about the equivalent dose as far as the amount of aluminum adding compared to alum at a dose of 80. So about 55, 57, it's about the same amount of aluminum I'm adding to the water compared to 80 milligrams per liter of alum that's dry that's being added. Now the filterability of this coagulant is very good, 0.04. This is the limitation of my instrument, so 0.04 is the best I'm going to read on my instrument. The settleability, just skip the UVA for a second, the settleability is a little bit better, 55.08, 0.132 at 60, and compared to say at 80 with it's 1.74, so a little bit better settleability. But the UVA wasn't as good. With the 80 alum, we're getting 0.032. With the 9800, in the high 0.3. So not as good as organic reduction. But what I would do is further investigate if I can increase this dose without affecting the filterability, and see if we can improve on this. So this would be. So I would do a further more jar testing just to see if I can, what's the best performance I can get out of this chemical. Because if you can get it down to point, down to at least what the alum's doing, and maybe better settleability, then the pros is that the advantage of this is that you're getting less solids loading to the filter. Also, this type of coagulant doesn't use up the amount of alkalinity that alum does. Alum, when you're adding alum, for every part of alum you're adding, you're reducing the alkalinity by half a part. So if I'm adding 80 parts of alum here, I'm reducing my alkalinity by 40, which is quite a bit. That means my pH is dropping, and so my pH is dropping, therefore after filtration, for corrosion control, I'll have to raise my pH back up, adding caustic soda, which this utility does. But if I'm using a different coagulant that doesn't lower the alkalinity very much, very little, maybe about 1/10 what alum does, then I don't have to add as much caustic soda to raise the pH up, if any. I may not have to add any caustic soda, or just not as much. So this product is more expensive than alum, but you're not adding as much caustic to raise the pH up, so you got a trade-off there. And then the other thing I do is just kind of post the pictures of what the jars look like after any of the flocculation process, along with the results. This is after 5 minutes after the water has settled, and then this is when I draw the water for the filterability. So it's plenty of flock to analyze, to evaluate the flock strength. And that's where the filterability does, is evaluate the flock strength and determine whether we got a weak flock or a strong flock. And then this is what the jars look like after settling. And you can look at, this is the first set of jars, you can tell that this jar is much better, clearer, because the settled water turbidity is 1.47, where it's up in the 3s and 2s here. So these are just underdosing right here. You've got to go at least 50 to get some kind of good filterability going on, but the organics are not good. So we go on to other jars, and this is going at a higher dose of 55 to 70. This is what it looks like at the end of the flocculation process. This is after 5 minutes. And then this is when we draw our sample for the filterability and UVA analysis. And then again, this is what the jars look like after 25 minutes of settling. And again, you can't tell just by visually looking. You need to look at the results. And so the UVA, the filtrate is 0.07, 0.07, 0.05, 0.05, under 0.1. Settleability are all about the same, but the main thing, one of the other parameters that we're really looking at now, once you get everything, once the filterability is all about the same, then you start looking at the UVA. The UVA here is 0.41, but over here is 0.035. This is going to make your chlorine demand is going to be less, and you're going to have less byproducts, disinfectant byproducts with a 0.035 compared to a 0.41. So if you're thinking, well, maybe I could save costs on chemical, well, you might save costs, but you're also it's also a better chance of being in violation of the disinfection byproduct rule. So so by doing that, if you're thinking that I want to save costs, you're going to find yourself in trouble because of disinfection byproducts. And then we go up at a higher dose. These are the jars at the higher dose, from 75 to 90. And this is after 5 minutes of settling. And then this is after 25 minutes of settling. Again, we're looking at filterability and also organic reduction, or UVA. So here we went from the previous jar was a little bit higher than 0.34, but now we went down to 0.034 at 75, and then 0.032, and you notice it's all 0.32, 0.032 for the UVA. So this tells me that we're at the limits as far as how much organics we can reduce. We're not going to get any improve with, at least with this product, with this acid alum. We're not going to improve as far as organic reduction. There might be other coagulants that might do a better job. You might, one of the things that can help improve this, get this value lower, might be a preoxidant like potassium permanganate if you have the contact time up front to use, or acid. We are adding acid because this is a blended coagulant that does have sulfuric acid. But there's other things you can do as well, like powder activated carbon you can add with the coagulant that can help improve this, but then there's also a cost associated, though, and how much improvement you're getting too, you have to look at as well. So so I'm looking at this and I'm thinking, okay, 80 is probably my max dose, and then we'll evaluate 80 again. And so the next jars I looked at 80 again, but I also looked, and I jar test each one at 80, but I also looked at the last 3 jars at a polymer that the system's using, which I mentioned earlier, and just to see what kind of impact it would have on the results, which it really didn't have any kind of positive impact. And so again, 0.032 at 80, filtrate 0.04, which is nice. So this is what it looks like after 5 minutes and after 25 minutes and so forth. So not too bad. 80 seemed to be the dose that the operator should be shooting at to optimize its filterability and organic reduction. And then the last jars with the different coagulant, we used a ACH, which is a 9800, and then a blend of ACH and polyamine, which is a 9890. So we did a 5560 by itself for the 9800, and then we did a same dose, but then we also added 3 parts of the 9890. So this is kind of what it looks like, and you're going to get a little bit different flock compared to alum as far as what it looks like. The settleability, though, a little bit better settleability than the alum. Not much, though. Just something you have to evaluate, whether a 1.08 or 1.32 is significant better than maybe a 1.6. But this is all relative, so this jar has the best settleability. Also has, it's all 0.04, so the filterabilities are all the same, but the UVA are not the best. So I would, again, further investigate this product just to see, how much higher I can go to and see what kind of improvements, if any, on the UVA results. Okay, part of jar testing is that we want to evaluate the filterability of the coagulant and dose that we're using. And here's an example of a system I was working with where they're using alum, and their dose, and we are dosing at, say, 46 milligrams per liter, and their filterability is 0.13, which I consider, it's not a great strong flock. I consider that a fair as far as, flock strength. And redid the dose again, same kind of results, 0.12, 0.13, so repeatable, and the flock strength is considered fair. And the goal is to get the filterability down below 0.1. So to do that, we can add what we call a coagulant aid. And in this example, we're looking at a polymer called a DADMAC. It's a polydadmac polymer. And so we do the same dose of alum, 46, and we start with a low dose of 0.5, and then look at the filterability, and it didn't change much, still the same. Start with 1, and we go same dose of alum, and then go with 1, a little bit of improvement, 0.11, and then 1.5, 0.08. Now we're getting below 0.1. Do 0.15 again to repeat the results, and it's still again 0.08, and then we get to 2, and we get down to 0.06, and then do it again at 0.05. So just by adding a polymer, that we can strengthen that flock up, meaning it makes it more stickier, stays on the filter longer when you have a weak flock. So we went from 0.13 down to, say, we can get down to 0.06, 0.05. The next example is just another system working with where we have dry alum, and they were they're dosing actually both alum and polydadmac, but one of the things I do first is just jar test the primary coagulant to see if the polymer or the coagulant A is necessary, or what kind of impact, what kind of results we get without the polydadmac. So we start with 35, go to 55. If you look at the, and they're dosing at 35. So, and we look at the filtrate turbidity, it's 1.06, very weak flock, and that's what they're dosing. But they're also dosing a polydadmac as well, but this is without the polydadmac. And so we go to 45, we go a little higher dose, a little bit improvement, then 50, more improvement on the filterability, and then 55. And so we can make improvements with the coagulant to a certain point, but this is still a weak flock. And so they're adding a polydadmac, and in a combination with a 35 and a 6. And by doing that, all of a sudden now we're at 0.08. So we go from 1.06 NTUs to 0.08 just by adding the polydadmac. However, they're still underdosing. If you went to 45 and 6, you get a better filterable flock, 0.05, and 50, 0.04, and 55, 0.05. So in reality, they can, by just going down to 45 with a 6, they're going to get a much stronger flock and a better filterability. So here's a slide, 4 jars from different times, seasonal for this particular plant. This is a plant that has a source water that has big seasonal changes in water characteristics. And we have water, we have algal blooms, microcystins. We have a vent where there's a rain event, so the water kind of looks like this. Then we have another algal bloom, limbaya, stringy algae. And then we have our drought. And this is from last year, what the water looks like. So this system can experience these different water characteristics throughout the season. And so when you have these changes, the operator can't just guess on what kind of, what the dose needs to be changed, or even what kind of coagulant they might need to try out or add with the primary coagulant they're using now. And this is a case where they need to do jar testing. They can't, they can't just be guessing, and by doing jar testing, they can quickly zero in what kind of, what coagulant or coagulants they need to add and what dose to be able to treat this water. In jar testing, we can look at, after you're all done, we can look at the filterability and UVA reduction. But if you want to verify, what kind of disinfectant byproducts we're going to get, we can compare what the plant's dose, the plant's coagulant and dose, with the optimum coagulant and dose based on the jar testing, and also look at other coagulants as well. So here's an example where a system is adding alum at 35 milligrams per liter and polydadamac at 6 milligrams per liter. And their filterability is really good, 0.04, but the UVA is poor. They have a 0.046. And what we do is that we'll take this water from the jar and we would filter it and then spike it with chlorine and then do THM-HA5 analysis. And at the same time, we're also running a jar side by side with the optimum coagulant dose. In this case, the dose was 80 versus 35 with the same polydadamac dose of 6. Same filterability, 0.04, 0.04, but the UVA is much better. It's a 0.03 versus a 0.46. And if you look at the results, then we kind of step back here. We also looked at a different coagulant. This is a sulfonated pack of 200 parts per million, or 200 milligrams per liter, with the same polydadamac dose. Same filterability, 0.04, and a little bit better UVA value, 0.03 and versus 0.029. And then also the difference is that the settleability for each one is the same. So we got the settleability for this 2 alums, around 2 NTUs for each one. But this other coagulant, much different coagulant, has a settleability of 0.42. And so we take these 3 jars, we will filter it and spike it with chlorine and do a hold time, and then do a THM-HA5 analysis on them after so many days of hold time. And as you can see that the alum, the system's current dose, produces a THM of 90 and HA5 of 63, which are both over the MCL for disinfectant byproducts. And by increasing the alum dose, we can now get well below the THMs for the MCL for THMs and also the HA5s. And then here we have almost the same results for the other coagulant. So if you look at the UVAs, they're almost the same, and therefore the THM HA5 values are almost the same. The next graph is just a chlorine decay rate graph, which this is the plant existing dose of 35 milligrams per liter with the 6 milligrams per liter of polydadamac. And its chlorine residual is pretty much gone after a couple of days. After almost 2 days, your residual is less than 0.1. But if you look at the other 2 coagulants, they're getting better organic reduction, therefore the less chlorine demand. They string out all the way out to over almost 6 days, 6 or 7 days for the where we just increase the alum dose, and a little bit longer, maybe about 8 or more than 8 days for the other coagulant. So there's a way in doing as far as jar testing where we can determine our best coagulant dose for organic reduction, but we can also take that water and do some THM HA5 analysis and see, compare the existing plant disinfectant byproducts with the existing plant's current dose and coagulant, and what the kind of disinfectant byproducts we may get compared with the optimum coagulant and dose. And this is a case where just looking at filterability is not enough. We have to look at where the filterability is the same of all 3 coagulants, but you want to look at the UVA. and see where you are on that. And the reason why their THM and HF5s are high because of the poor removal of dissolved organics. To be optimized, this is right here what they would need to increase from 35 parts to 80, which is a lot, but this is what it takes. You know, if you want to remove organics, you know, you're not just optimizing for the filterability like we used to do maybe 25 years ago. We didn't care so much about disinfectant byproducts, but now we do. Now you need to do what we call enhanced coagulation, where you're adding as much coagulant you can to reduce as much organics as possible in the source water to minimize disinfection byproducts. So here's a case study where we're comparing the treatment plant's coagulant dose with the optimum coagulant dose based on the jar tests we did. And the measurements we did is a UVA, chlorine residual, and disinfectant byproducts, the THM and HA5s. So here's a case where this facility was adding a certain coagulant. Right here is a ACH, and it's a blend, a polymer blend of ACH and polyamine. And they're dosing about 1.8 milligrams per liter. The filterability is 0.09. And their UVA is 0.032. Their THMs, and then based on the jar testing, I came up with, to improve on the UVA, we increased this dose from 1.8 to 2.8, but also adding another coagulant as well, as a sulfonated pack. And with this combination, we're getting a better filterability. So we're going from 0.09 to 0.04, and much better UVA value. Basically, we're removing twice as much indirect DLC from the source water, compared with the existing coagulant and dose to the optimum coagulant dose, and by adding this other coagulant. So we go from 30% to 63% reduction. And then we take these 2 jars, we spike it with chlorine, and we held it for this one 6 days. And you compare do the analysis, and the THMs, HF5s were 71, 41. So this is, pretty close. You're getting close to the MCL for the disinfection byproducts. But then you can see the difference between the existing plant results versus the optimum coagulant dose, and adding this other coagulant, where we go from 71 to 44 and 41 to 29. And after 6 days, this is the chlorine residual for each one. So less of a chlorine demand because there's less organics in the water. And this is just a graph that shows the chlorine residual on the y-axis and the days on the x-axis. And the bottom, the blue line, is the existing plant chlorine decay rate over time. So after, say, 11 days, you're down below 0.1 milligrams per liter of free chlorine. But then after 28 days, this system went over twice as many days and still has a higher chlorine residual. And so this just shows you that the more organics we remove, the less disinfection byproducts are producing, the longer, and also less of a chlorine demand on the system. So this is just a comparison that you can do with also with jar testing. Is once you determine your optimum dose, you can actually go further and looking at and compare the THM-HA5 results as well. So these are the plants that I work with over the last number of years. They range from conventional treatment to direct filtration, to dissolved air flotation, to Triton, the Roberts, the ActiveFlow, and then we have alternative technologies that are like the roughing, contact clarifier media, and light filtration. So all these are all different types of plants, and so conventional plants are the only one that have settling. And I worked with about 24 of those plants from 2018 to 2021. And then the rest of the plants are or the direct filtration and dissolved air flotation and so forth. And so if you look at the rest of the plants, you know, half the plants don't have settling. And so this is just to show you that people that have been trained in doing jar testing and just looking at settling, you wouldn't be able to, first of all, settling doesn't provide any kind of supporting data for filterability and organic reduction. It just tells you how well something's going to settle. But if you're working with direct filtration or any of the other plants, there is no settling, and so you need to have a jar test that provides data on filterability, like flock strength, and organic reduction.